I appreciate you guys having me here, and I hope I meet your needs. And I'll explain my understanding of what you had requested here in a few minutes. So my presentation might be slightly different than some of the priors that are trying to meet the same goals. So from my experience and knowledge, what I wanted to bring forward were some ideas and research needs for Lifeline infrastructure systems to improve seismic design codes and standards and meet some of the knowledge gaps. And I know that the purpose of this workshop goes beyond that, but I do have limitations. And as you noticed from my bio, my expertise is really in water systems, but I did help. I've worked in Lifeline Systems in general for quite a while. I did work for the Department of Water and Power, and I was the resilience manager for the city, which incorporates all of the Lifeline systems as well as other community systems that Professor Vandelant had brought up. So my knowledge base does go beyond that, but I am not an expertise in all of these Lifeline systems. And also, I played a significant role in the American Society of Civil Engineers for helping to initiate and develop the current infrastructure resilience division, where we look at all of the Lifeline systems, as well as prior to that, the Technical Council on Lifeline Earthquake Engineering. And some of my mentors were the founders of PEAKLE for ASCE. And so I'm trying to bring forward a broader perspective than just my own personal experiences, because the topic is Lifeline systems. And I'll get to that in a little bit. So here's the outline of what I'm going to talk about: Lifeline systems overview, some current challenges, at least as far as I understand them, resilience, direction in current developments, some research needs applicable to this testing facility, and then some conclusions. So unlike all the prior presentations, except for maybe CIFI, which was a little more general, geotechnical structures, Lifeline systems are a broad group of systems. So I'm not talking about buildings. I'm not talking about geotechnical structures. I'm not talking about bridges. I'm talking about water systems, wastewater systems, stormwater systems, electric power systems, communication systems, gas and liquid fuel systems, transportation, although I won't get into the specialty area of bridges, but transportation systems as a whole on all of the modes, and solid waste systems. And these systems have to work for the community, and they're social technical systems, meaning that you have to have the people who manage them interact with the technical components, or they don't work at all, right? These are to provide services to the community, and they're very broad. So they are large, geographically distributed systems. They're made of numerous interlinked and specialized components, which include bridges, which include buildings. So when I talk about components, in my language, a bridge, even though it's a system into itself, as just elegantly explained, is a component. A building, which is a system into itself, in a Lifeline system, I'll talk about it as an individual component. A dam, which could be a geotechnical structure, or the levees, right, or even the foundations. These are considered components in the Lifeline system, right? So in a water system, you'll have a dam holding back a reservoir, which is for a water supply system, which connects to the bigger part of the system. But that's just one component in this larger context. So these systems are interdependent.
Excuse me, Craig, excuse me to interrupt you. In case you are showing a slide right now, I don't know if you started to show a slide. We don't see it.
Oh, no. I'm actually, are you still on the very first slide?
No, we don't see any slide. I think did you double click on share screen? You should
I did. I'm sorry, I should have asked.
Okay, I think it's coming. Yeah.
Oh, I should have asked. All right. Well, you've missed half my presentation. That's all right. Not quite that. All right. So
you may want to put it in presentation mode, Craig. I'm so sorry.
Well, it was at one time.
Yeah, it's tricky.
I apologize for that. I should have asked. Come on.
Yeah, the button that you, but now it's back out. We don't see it again. Let's see, try to do it. And if you just click the presentation mode now.
Yeah, the problem was my, there we go.
Yeah,
There
that's
you go.
good.
Yeah, great.
Yeah, the internet stuff was in the way. Okay, so most of that verbal stuff had some language to go with it that you could look at on your own if you wanted to understand better. So what I was leaving with were these. So I just explained what Lifeline Systems are here, and I have them listed in the social technical systems. And I was going over this slide here, where there are numerous interlinked specialized components. They're interdependent, and they consist of a variety of subsystems. So even though I was explaining the components, like dams or certain structural systems like bridges or buildings, or in my language that I'll be describing here are listed as components. There are also these components that make up subsystems. So as an example, when I'm referring to subsystems, if you have a water system, subsystems will be the supply, treatment, transmission, and distribution. Again, all of which could contain these components, right? So in a water system, a tank or reservoir is a component of one of the subsystems. A treatment plant, which is a massive system into itself, is a component of the treatment subsystem, and so on for transportation and all of the other systems. They all have a variety of subsystems, and these subsystems all have separate owners and operators. So, for example, one company might own an oil refinery. Another company might own the oil and gas extraction facilities, and different companies would own the pipes or the transport systems to move this to the refinery. Then somebody else might own a different set of systems to move the refined products to places of distribution and so on. So all of these have to coordinate and work together, even in a disaster, or you don't get the services that you need. So these are complications of Lifeline infrastructure systems that either don't exist in the other types of components or systems that we've been talking about, or they're scaled up to be much more dramatic. So we have to keep that in mind when we're talking about Lifeline systems. There we go. Okay. So some current system challenges. There are limited codes and standards governing seismic design of Lifeline systems. Some of these are well developed, like we just saw in bridges and in buildings. And some are completely non-existent in other systems or for the components, right? And even though we have bridge design well developed in many areas, the seismic design of the transportation system as a whole, the whole highway system, is not well developed to be resilient, for example. I don't know if there's actually a seismic design code or standard for how the entire highway system is supposed to perform. As an example, there's inconsistent approaches and criteria within a single system, or across, and especially across systems. So in water systems, you got tank design, you got pipe design, but they're not necessarily, these different standards are not necessarily linked up to the same performance objectives. As an example of what that means, there's a wide range of regulations. So for some components or systems as a whole, there will be limited to no regulations. And in others, just for certain components, you might have multi-jurisdictional regulations. Like in California, for dams, there would be FERC and the California Division of Safety of Dams, both looking at the same structure. So, and highly regulated. So we have a wide range of those issues. We need to create resilient lifeline systems consistent with community resilience. John Vanderlint brought this up. Cissy brought this up. So we need community resilience goals, but they're limited to non-existent in most cities. And right now, they're kind of left up to if a city wants to do this. And Lifeline systems provide services to make these communities resilient. But right now, they have to develop them on their own if they want to claim that they're a resilient system. And there's very limited guidance on And then the disparate recovery-based goals across Lifeline systems, if they exist at all. And then we have the NEHR functional recovery, which is part of the reauthorization. And since you brought up functional recovery and gave an example of some of that in her presentation earlier. So then let's get a little bit more into Lifeline system resilience. It's multidimensional. There's lots of dimensions, but I'm going to give you just an example of three very commonly understood for resilience: robustness, redundancy, rapidity, and resourcefulness. These have been referenced in some of the earlier presentations as well. And thinking about physical testing, I thought about, well, what is it that we're looking at? So remember, we're talking about resilience of a whole system, not a component. And so robustness of the components is usually what we're talking about for physical testing, or some of the combinations of components and how they interlink. Sometimes we're talking about redundancy. So redundancy in the bridge system was just brought up quite well. But when you're talking about a system as a whole, you might be talking about two parallel transmission lines coming from two different sources of power generation. Right? That's also a redundancy. And so it's not redundancy within the same components, but redundancy within the system as a whole. And we may include some aspects of rapidity and resourcefulness, but without all of these, you can't have a resilient system. So physical testing is important, very, very important, but insufficient to create a resilient Lifeline system, right? Because we have to have all of these other things. So I just wanted to have everybody keep that in mind. And so now some current momentum in Lifeline earthquake engineering. There's a big push and developments for a framework for recovery-based objectives that will be consistent across all Lifeline systems and buildings as well, buildings and systems, to develop and improve existing codes, standards, and guidelines. So I separate here develop, because I mentioned that some don't exist, and to approve existing, right? And all of these have to be done on a consistent with the framework, which is why the framework is bullet number one. Then establish design levels so that systems can meet the recovery-based objectives. Establish the design levels for each component can ensure the system meets, right? So that fourth bullet is to support the third bullet, because resilience is a systems level concept. And then define how to meet the objectives by designing new components, subsystems, and systems, and modifying the existing component subsystems. Right, so these are some of the things being worked on. So now what I'm going to do is go through some research needs. And I'm going to talk about it at the Lifeline system level and some key components to give examples. I'm not going to be able to talk about all of the different Lifeline systems and all the different components, and I'm not intending to. I'm not going to talk about all of the different types of materials that can be researched, all the different types of structural systems that could be used, or the geotechnical systems that could be used to improve the Lifeline systems and their resilience, and all of that's implied, right? So I'm talking about at a higher level. So when I'm talking about pipelines, for example, there's a wide variety of pipelines, and new materials can be made, and all of those can be embedded into these research concepts that I'm bringing forward. So keep in mind the level that I'm talking about, and use your imagination as we go forward, and understand that this is just to give some ideas. There's no way I could talk about all the different types of things that need to be done for all of these different systems that are made up of all these different unique components, right? So research on specialized equipment. Here, I'm just going to give some examples. Wind turbines, which have already been tested, but wind turbines tested in multi-directional shaking. It's going to be a huge difference. So I should have probably gave an example of the Los Angeles Reservoir outlet tower, which was about 80 feet high, shaken by near-source pulses in the 1994 Northridge earthquake. A recording on that showed that it circled with 1G shaking 10 times. That's very different than, right? So it was just swinging in a circle 10 times with 1G at the top. That was recorded. So imagine this with this windmill doing that, not just two-dimensional shaking, but three-dimensional. It's quite different. So it's really important to take a look at that. Communication towers, they have different masses changing all over in the connections for those. Pipes and turbines, I show a vertical turbine down at the bottom, right? So heavy mass at the top while it's spinning. There's large valves that are I'm showing in the middle of UV ultraviolet treatment plant for the Los Angeles Department of Water and Power. But what I'm showing here is that it could be a smaller vault of just one line or these large systems. But think of a very long pipe that might be miles long that comes from the ground and then passes without being anchored to the wall, right? It's just an opening that collects axial strain from wave propagation. And now you have inertial shaking going in the opposite direction as with flexible connections and so on, and rigid connections where you have these multidimensional movements that have never been analyzed before that's affecting this, which looks like a simple structure, but if you were to look at it in greater detail, you'll see all these different types of connections on this one single pipeline and the things that are going on. So things that have never really been fully addressed but are probably important. And then you see just some wastewater filters. If you blow that up here on the left in that image, you would see that it's actually quite a set of complicated structures into themselves, right? It's made up of a bunch of different things that need to not be broken during an earthquake. So think of also traffic control towers at an airport, right? A very large type of structure that you could analyze. So Lifeline Systems are made up of these components of above and below ground specialized things that all have to work intimately together. And just a wide variety of different types of things that are affected. Then there's the interaction of multi-system components. So think of this large table as an opportunity to put multiple portions of a subsystem together. So you saw actually there was an example that Joel pointed out from a power cable on a few poles, right? So that would be a small portion of these examples that I'm showing on the right of this diagram. But then there's brittle insulators, and then you could use different materials to create flexibility on that. And there's rigid connections, and there's how much sag you put in the cable lines, and all of this moving in 3 dimensions makes a big difference on how these systems perform. So with this table, you can either use full scale or maybe scale them down and put multiple components and how they actually interact, because they're all interconnected in Lifeline Systems. They're not individual buildings that could just sway and hit each other if they're too close, but you would walk in between them, or maybe you have a bridge. But all of these systems are connected together. So also think of the complications of an oil refinery, right? Again, one component, just like a substation, but it's made up of all these intricate components. And look at these big towers and things that are interconnected. Very unique structures, but really, really important to Lifeline Systems. Think of the underground piping in water, oil, wastewater, natural gas systems, and how that might be analyzed when it's affected by liquefaction. I'll get back to some of that in future slides here. But just to give some ideas on the importance of looking at the subsystem. Then there's the interaction of multiple system components, including both shaking and differential movement. And these differential movements might be ever so slight, but I'll give you some examples here in this slide of how important it could be using some rigid electric power connections. So here's an example from Lushan, China, from the 2013 earthquake that I investigated. And what we have is an electric power substation being supported on one side by a gravity retaining structure. And then above that, you have just a vertical wall that was unreinforced and it fell over. That's not the point that I'm talking about. You do see that on the lower left structure. What I'm talking about on the lower left picture is the gravity retaining structure that's down below. It's quite high, maybe 15 feet high. And then it's supporting a portion of this electric substation. On the right, what we see is near the margin of what happened where the ground cracking occurred because the gravity retaining structure had moved. We see ground cracks. They moved anywhere from just fractions of inches to accumulation of maybe 6 inches. But if you take a look at the equipment that's in the lower right image, you see that there's damage in some of these flexible and rigid connections. So some of these were actually flexible, but not flexible enough. Well, I don't know that any of the codes or standards for electric power, and I could be wrong, I'm not an electric power expert, but I have asked around, how much do they actually account for permanent ground movement? And so now we have multiple issues that should be tested with shaking, as well as when permanent ground movement occurs. Or if the shaking's not at damage, then maybe the even small amounts of permanent ground deformation should be accounted for. So as one idea. Now, Joel assures me that this equipment could actually be used for fault rupture. So I just threw out some ideas of some potential near full-scale or full-scale testing that might be used. One of those might be to confirm tests on underground piping that have been done at the Cornell box that they show an image of in the upper right. They've done a tremendous amount of work on pipelines, maybe between 6 and 12 inches in diameter, but a lot of the Lifeline underground systems go much larger than that. And so on this test bed, you might be able to confirm the behavior or disconfirm the behavior of larger diameter pipes compared to the smaller diameter pipes. And then put that in a numerical modeling method so that we don't have to test all pipes and all the different types of liners and materials and jointing connections that can go with that, right? There's a whole bunch of stuff that can be done on large diameter that so far has not been able to be validated because we can only test the smaller diameter. But that would be a tremendous help. Then the behavior of co-located lifelines. So I show an example of lifelines crossing the San Andreas Fault. So here, with this large test bed, you can vary and just statically, well, semi-statically or quasi-static move a fault rupture, but you could actually look at the interaction of multiple closely spaced underground structures and how they affect each other. That I don't believe has ever been done before. Then we can take a look at tunnel liners. Right? I show 2 examples of different types of tunnel liners, concrete and steel. But there's a wide variety of these. But we're putting railways and tunnels through faults, and we're designing for that. But we really don't have a good understanding of how these different liners behave, or even if they'll collapse from real testing when they're ruptured with the shear or thrust movement. And then I don't show an image for this last bullet, but there needs to be a better understanding of how fault ruptures from a rigid bedrock, base rock, ruptures up through weaker soils, including potential liquefied soils up above, and how that affects the shallow buried structures, the Lifeline systems above that, right? So things that I think maybe could be used. Then there's an idea of that in the Lifeline industry, we're using margins of landslides are assumed to behave similar to a fault rupture. So if you have a strike slip fault, that's kind of the vision of the way we look at margins of landslide. But there's a landslide actually has 2 margins, right? So the width of this landslide is really important. We really don't understand how this interacts with the stresses and strains in buried structures, right? So especially when we're looking at moving pipes moving across a landslide or cables or any type of buried structure transversely, longitudinally, or especially obliquely, right? These types of things maybe could be tested in a test box that could simulate landslide movement. Or if you could do 2 shear movements, like 2 fault ruptures at once, I don't know. But just some ideas. I don't know if you could accommodate this, but some things that would be really helpful. And to confirm if this concept that you could just use the fault rupture as a margin of a landslide and simulate things this way. Then liquefaction. So in the lower right, I show this is an 8-foot diameter pipe that buckled from liquefaction in the 1994 Northridge earthquake. You see this 8-foot pipe buckled to this is actually my PhD dissertation, and my fingers, which are not really very wide, could not fit between portions of this. They're completely buckled to 0 dimensions. So what are the mechanisms behind this that could be tested? The mechanics of uplift and floating. There's lots of discussion on this. How important is this? Although I'm showing a sewer pipe in the middle and with the Hope earthquake where it's uplifted several feet. But in different types of varied systems, there's discussions on the importance of this, and that could be investigated. And then the effects of lateral spreading on varied pipe networks. So here I show an axial pipe, which is the most common analysis of an infinitely long pipe moving or varied, and the lateral spread occurs along the axis of the pipe. But in reality, we're not analyzing a network, which I show here now. That it's a network of distribution pipes that are with T's and L's and valves and all kinds of connections and press blocks and all kinds of things going on. That's not been investigated. I don't know if you could use this larger set of testing equipment to simulate a lateral spread and the margins of that lateral spread and how it affects an entire network scaled to some level. You might actually be able to use full scale if you use 2 to 4 inch diameter pipe. I don't know, but just an idea that you might be able to undertake. Wave propagation. So Joel was talking about the rocking motion. He had mentioned that to me a few weeks ago, which brought up a thought in my head. I don't know if you can simulate Raleigh waves on this machine, but that would be pretty awesome if you could, because there's a need for better understanding the strains in the ground caused by Raleigh waves, surface waves, and how that strain propagates into pipelines so that we could better understand the design of varied pipelines subjected to surface waves. So I'll throw that challenge out to you. I don't know if that's possible. I'll also, on this next bullet, I'll show an image in the next slide. But so lifelines, a lot of times come up with long linear lines, usually pipelines, but there's are of importance. But you got long cables, you got very long structures and such a stuff. So I don't know if this table can simulate differential movement at each support, but I thought about that over the past few days, and I think you could. So we have multi-supported pipelines or other types of cables and so on. And we need to investigate the behavior of the different types of support. So think of a bridge, right? We just saw long span bridges with multiple supports, but these things go miles and miles and miles. So we need to understand how that is affected. These structures are affected by how a wave propagates through this. So think of the Raleigh surface wave propagating along the length of this, or oblique to it. So there'll be multiple piers with simple foundations or piers. Those piers might be deeply connected. Those different types of connections and foundations need to be identified. And then say, for example, you have a pipe on this pier. It might be a saddle pier where the pipe is just sitting on it, or it might be rigidly connected to this, right? So we have all kinds of different motions taking place. So we need to address how these different connections affect the behavior of the structure and how a wave propagating through there changes all of this, right? So let me give you an example of this in an image. So in the major part of this picture, what I'm showing is the Los Angeles Aqueduct in the north end of the San Fernando Valley. It was severely shaken by, at the time, both times, record-breaking ground motions from the 1971 and the 1994 Northridge earthquake, but never damaged. But what you see here is there are some, I don't know if I could put the, I don't know how. There we go, you can put a laser. So we have saddle supports here. So think of a concrete pier that's going about a quarter of the diameter. It's curved, and it's cast in place, curved. It's just sitting on the ground with just bearing on the ground. And so this pipe is just sitting on it. There's no saddle support. It's not rigidly connected. It's just sitting on this concrete pier, right? You just see them up in here. A little bit easier. I probably should have blown up a picture for you to take a look at that. But with very large accelerations, reaching or exceeding 1 G, very large displacements reaching or exceeding 1 meter or 3 feet, and very large velocities reaching 180 or greater centimeters per second. This pipe was not damaged in 2 earthquakes. But yet, structural engineers want to come in and make these rigid connections. Deep foundations, replacing these piers with on piles and putting rigid straps around the outside. So it would be really important to understand, how does this pipe actually rock as it's sitting in this pier, because it's not connected? How does this pier actually rock on the ground, right? It's not rigidly anchored into the ground. And then how do those different motions change? And we have this long structure with each pier rocking differently, and it's torsionally moving, right? So this happens to be a riveted steel pipe, so it's actually able to move at each joint connection. It's not welded steel, which would accumulate more stress at each weld. So all of these different things play a big difference, and we do not understand this, but yet engineers are changing things based on what they think current philosophy is, which is rigid connections, as opposed to flexible connections, which are proven to be quite useful, similar to the bridges discussed earlier, and past experience. So all of these things really should be investigated further. Maybe have an opportunity here. And then we have water sloshing, right? So we have treatment plants with different tanks of water, and I'm showing some examples. I don't know if you could put a water tank and simulate some of these things, but we have sensitive structures that could be affected by water sloshing, baffles, clarifiers, and so on. We have surge pressures in large water pipelines and their effects. So we have these long pipelines that move around. Somehow there's a generation of surge pressures from the shaking, which isn't well understood. And then we have connections to these. And I'm showing an example of an air vacuum valve that have a ball. So in past earthquakes, these balls have been completely crushed by the high level of pressure that is generated. So another idea of maybe things that could be investigated. We have varied box structures, very common types of structures in Lifeline systems of all types. And so I'm showing a box structure, which is a long linear, saying infinitely long in the lower right, which is actually a task that was done in the past there in San Diego using the earlier version of this. And I'm showing a box structure that has shear walls on the side. It's a true box, right? It has an end cap. So the blue would be actually an end to this. So think of a large vault or building type structure underground. And so the top behaves as a diaphragm, the bottom behaves as a foundation of some kind. There's deflections in there just from the diaphragm. They have varying dimensions of height, length, and width. But as those dimensions, right, so you have a very rigid at the shear walls in the lateral direction. The shear walls don't move very much, but if this is a very long span, you're going to get the middle moving a lot, right? So that's the displacement of the diaphragm. But as we know, soil pressures are a function of, on a wall, is a function of the displacement of that wall. So we get varying deflections and varying pressures along these structures that are not well understood. And are we properly designing these right, would be my question based on this basic concept. These are questions that come around in the industry. Then we have really complicated underground structures. I just show an example from the internet of how complicated these subway stations might be. And so think of the things that John Vanderlint presented for above ground multi-story structures. Now put that underground with escalators and elevators and stairways and multi-levels, sometimes 3, 4, 5 levels of subway stations in some of these things. So they can get very, very complicated, and these aren't well investigated and maybe could be tested. So in conclusion, I'd like to remind you that Lifelines are very large, complicated systems made of numerous specialized components. There are limited code standards and guidelines dictating their seismic design. There is a need to create and improve standards incorporating recovery-based design consistently across all Lifeline systems. Several potential research ideas have been presented, but I don't think that I think I'm just barely touching the surface. Hopefully, I've sparked some imagination for people to utilize throughout all of these Lifeline systems and specialized components. And you can come up as experts in testing. You can come up with ways to utilize these advanced testing machines that you have to improve the performance of Lifeline systems into the future. So thank you, and hopefully I haven't gone overtime, and so not much. And I'm sorry for the confusion at the beginning.
Thank you very much. Appreciate that. If there's any questions, please feel free to put them in the Q&A. I see one question here. I'll read it out. What about nonlinear numerical modeling considering SSI and asynchronous motion? The size makes the problem very complicated. How do you address
it? It should be incorporated, first of all, because things behave non-linearly. The question makes me think of my example of the long linear structures, and the numerical modeling of that can begin to give you ideas, but I think that the problem, even though it might seem simple, is much more complicated than what you're going to be able to know how to vision and imagine in just a numerical model. So my suggestion would be to incorporate that with testing. And so good numerical modeling in research and in practice with testing that uses practical aspects of what is actually incorporated in the field, similar to way good ideas on this were described in earlier presentations. The coupling of that is what I think we need. So hopefully I'm answering your question.